In this question, we're going to be figuring out the cell potential of a non-standard cell. In this question, we're carrying out a reaction between bismuth and rhenium in an electrochemical cell at 25 degrees C under non-standard conditions. Non-standard means our concentrations are not equal to 1. Our first step is to balance our equation. To do that, I'm going to write down my half equations for each of the elements. So for bismuth 3+ on the left, we end up with bismuth solid on the right. So we need to add 3 electrons on the left so that will cancel out our charges on the left to give us 0 charge on the left and 0 charge on the right. Then for rhenium, we start with rhenium solid. We end up with rhenium 3+. And so we need to add 3 electrons on the right here so that the total charge on the right is 0 and the total charge on the left is 0. Now, in order for our overall equation to be balanced, we need to be transferring the same number of electrons on the left and right side of our equation. We already have 3 electrons on the left and 3 electrons on the right, so we don't need to multiply these by anything. I can just have one set of each of these, and we can go ahead and add those together. So I've got one set of bismuth 3+ and one set of 3 electrons on the left. I've also got rhenium solid on the left. And then on the right, I've got one set of bismuth solid, and I've got one set of rhenium 3+ aqueous, and I've got one set of 3 electrons. So we can see here we've got 3 electrons on the left and 3 electrons on the right. So those are going to cancel out. And there's our balanced equation, and 3 electrons were transferred. So we can go ahead and fill this in now. We just have one of each of these to balance this equation. Okay, so there's our balanced equation. We've also been given E0 cell, the standard cell potential, if we were under standard conditions with 1 molar solutions, and we've been given K is 10.3. Next, we need to label the diagram with the concentrations of bismuth 3+ ions and rhenium 3+ ions. So we're told that in this solution, we have a 0.0359 molar bismuth sulfate solution. Now we can see here it's Bi2SO4 3. So when that splits up into its ions, we're going to get 2 Bi3+ ions, and we're going to get 3 SO4 2- ions. So if our concentration of Bi2SO4 3 is 0.0359, the concentration of bismuth 3+ ions is going to be twice that. So we're going to need 2 times 0.0359, which is going to get us a concentration of 0.0718. So that's our concentration of Bi3+ ions. What about for rhenium 3+? So again, we have Re2SO4 3. So again, when that splits up into its ions, we're going to get 2 Re3+ ions, and we're going to get 3 SO4 2- ions. So if our concentration of the salt, the compound rhenium 2SO4 3, is 0.370 molar, we're going to have twice that for the concentration of rhenium 3+. So it's going to be 2 times 0.370, which is 0.74 molar. So we can go ahead and fill that in here. Awesome. Okay, so we have our concentrations of our 2 ions. Next, we need to write an expression for the reaction quotient Q for this reaction. Remember, this is exactly the same as writing an expression for the equilibrium constant. The way that we do it is by putting in our concentrations of our products on the top to the power of their coefficients, and on the bottom we have the concentrations of our reactants to the power of their coefficients. Remember, solids and liquids are not included in this equation. Now in the products, bismuth is a solid, so that's not going to be included in our reaction quotient expression, but rhenium 3 plus is aqueous, so that is going to be included. And the coefficient is 1, so it's just to the power of 1, which doesn't affect it, so we don't need to include that. We're going to divide that by bismuth 3 plus, that is in solution, so that can be included. Again, its coefficient is 1, so it's just to the power of 1. And rhenium solid, that doesn't appear because it's a solid. So we can go ahead and fill in our expression now. We've got rhenium 3 plus and bismuth 3 plus. Awesome. So now we can go ahead and put in our values for our concentrations to figure out what Q is at the moment shown in the diagram. So the concentration of rhenium 3 plus we calculated was 0.74. The concentration of bismuth 3 plus we calculated as 0.0718. So if we put them to our calculator, we get a value for Q of 10.3. So we can go ahead and fill that in here. For Q, we got 10.3. Okay, now we're comparing Q and K. So K was also 10.3. So at this moment, Q and K are the same. Q is equal to K at this moment. And when Q is K, our reaction is at equilibrium and it won't proceed in either direction. So the answer here will be neither, it is already at equilibrium. Our next step is to calculate the instantaneous cell potential at the moment shown in the diagram. So let's head to our reference sheet. Here's our equation for non-standard cell potential. E cell is equal to E naught cell minus RT over NF ln Q. So let's go ahead and find all of our known variables. The standard cell potential, we were given that in the question. It's 0.02 volts. R is the molar gas constant. Here is R on our equation sheet. R is 8.31 joules per mole Kelvin. Then we need our T, our temperature. In the question we were told this is happening at 25 degrees C, but we need that in Kelvin. Kelvin is degrees C plus 273. So to get our temperature in Kelvin, we're going to take 25, we're going to add 273, and that gets us 298 Kelvin. So there's our temperature. N is the number of electrons that were transferred in our reaction. We figured out here when we wrote out our half equations to balance our equation that 3 electrons were transferred. So that's N. F is Faraday's constant. Here's Faraday's constant on the reference sheet. F is 96,485 coulombs per mole of electrons. And finally, Q is what we already calculated from our expression for Q and the concentrations given on the diagram. It's 10.3. Okay, so we can go ahead now and calculate our cell potential by putting that all into this big equation here. So let's do that now. So our standard cell potential was 0.02 minus R, that's the molar gas constant 8.31, times the temperature in Kelvin 298, divided by N, the number of moles of electrons transferred per mole of reaction, which was 3, multiplied by F, Faraday's constant, which is 96,485. And that's multiplied by ln of Q, which is 10.3. I've got 0.02 minus, and if I put all that in my calculator, I get 0.0200. So I'm doing 0.02 minus 0.02, which gets me a cell potential of 0 volts. So let's go ahead and fill that in over here. So what was the instantaneous cell potential? Well, it was 0 in the end. And that makes sense because K and Q are equal to each other. It's in equilibrium. That means neither the forwards nor reaction are happening. So our E cell must be 0. Finally, we need to compare E cell with the standard cell potential at the moment shown in the diagram. Well, in this situation, we said E is 0 because Q is equal to K. So this equation was used to verify what we did conceptually in the previous skill. So we have a lot of steps in this problem. We start by balancing our equation by writing out our half reactions. Then we're going to calculate the concentration of our ions in our solution. Next, we're going to write an expression for Q and substitute in our concentrations to calculate Q. Then we're going to use that Q value in our equation for the instantaneous cell potential, along with N, the number of moles of electrons transferred per mole of reaction, the temperature provided in the question, the standard cell potential, and the constants molar gas constant and Faraday's constant. We're going to put those all into our equation to calculate the instantaneous cell potential at that moment. And what we'll find is that matches up exactly with what we predicted from the previous conceptual skill.